Hello class, and welcome back to Calc 3. This is Dr. Ernie recording in his bedroom office. I apologize in advance for the quality of these lectures. I don't have a professional podcasting or vlogging setup. I'm just recording this with my iPad. I wanted to start the class by having some remarks on the coronavirus and how this is going to affect the class. The first things I want to emphasize are to stay in touch and communicate your needs. That's this first dot. I get a little laser pointer. That's how we're gonna follow things as I write on this. So please stay in touch and communicate. Send me emails, post questions you have on the class forum where we can reply promptly to them, me and Reeve. And please be, we're planning to be as accommodating and flexible as possible. That's point 2. So if problems come up, or if you have questions, or I say something in a lecture video that just doesn't make sense, make a comment, ask a question in the forum, and I will respond. I might make little addendum videos where I clarify things. This is all possible because these aren't pre-recorded mass-produced lecture videos. This is just me talking to you, but far away where I can't infect you with anything. So some examples of things that students have already kind of started talking with me about, or I'm anticipating. So people are traveling a lot in the next week or two as students return home, if you aren't already, and I know there are lots of international students who may be traveling a substantial different distance and being quarantined upon arrival in other countries until they are sure that they are safe. If midterm 3 is at a weird time for you and your schedule, please let me know. It's going to be administered at a distance and online. I'm hoping I'll be able to give it to people both in advance and late, as needed to make accommodations for everyone's, issues during this time. So if you don't have a smartphone or some other way to submit the exam online, you can talk to me. My hope is that people will be able to submit them with their iPads if you have an iPad, or by printing out the exam and writing on it and then taking a picture with their smartphone and uploading a scan, or just writing their answers on a piece of paper and taking a picture with a smartphone and uploading a scan of that. I will talk more about this as we get closer to the exam. But if those things are not options for you, because of internet availability and smartphone, etc., talk to me. Send me an email. We will figure something out. If you are sick at any point in this course, or you are caring for ill relatives and you need extensions on homework, please just reach out to me. Do not worry that is that is an inopportune request. This is what we're dealing with, and I expect a lot of people to have unusual stresses in their life as a result of the coronavirus. So I just want to stop and say, please contact me. We'll make things work. I want to start talking about math and hopefully helping everyone return to some sense of normalcy in their life. So let's talk calculus. I realize that I have one more pretty big announcement to add, which is read the announcements on Carmen. I'm recording this lecture during our extended spring break already. I anticipate that in, 1 to 3 days, there's going to be other things that I need to tell you about, and the announcement section on Carmen will always have the most up-to-date information. So, let's talk about calculus. Today we're talking about cylindrical coordinates. So, I've written down here the key formulas I want everyone to memorize. Let's take a little zoom in. Over there on the left-hand side, they're highlighted. You should think of cylindrical coordinates as polar coordinates in the xy plane and a z coordinate. So if you're good with polar coordinates from what we did before spring break, you're already, 9/10 of the way to using cylindrical coordinates. And I'm going to emphasize that as we go on. So the key formulas to memorize over here on the left-hand side, we've got our new volume form. So dV, which is going to stand in for, not what it is in Cartesian. So in Cartesian, it's dV equals dx, dy, dz, or some combination of that. In cylindrical coordinates, it's going to be r, dz, dr, d theta. Most of the problems in cylindrical coordinates make the preferred axis the z-axis, this one that's not in polar coordinates. Sometimes you have a setup where you want to make the x-axis the preferred axis, not the z-axis, and we'll talk about that if it comes up in any examples. But, in your brain, you could think z-axis is up, and that tends to work for these problems. The x and y substitutions that we have, these are the same as what they are in polar. And part of the dv, the portion of dv that was dx dy turned into r dr d theta in cylindrical coordinates. So in some sense, if you already have memorized the polar substitutions, x is r cosine theta, y is r sine theta, and dA is r dr d theta, which is dx dy, then you're done. Now we're just adding a dz onto things for the d volume forms. So dx dy dz becomes r dr d theta dz, but it tends to be written as r dz dr d theta because that's our preferred order to do the coordinates in. And the x and y's just use polar substitutions, r cosine theta, r sine theta, and z stays the same. So what this means is if you're describing this green point that I've highlighted, you imagine that it's living on some cylinder of some radius around the xy plane. So you put it on the surface of a cylinder, and that cylinder can expand or contract depending on what green point you're representing. And you look, okay, where is this point? And you drop down and you say, okay, in the xy plane, that point has some image, some shadow underneath it, which are just its x and y coordinates. So this point might be x, y, z, and now down here I'm looking at x, y, 0, right? That point, convert to polar. So in the xy plane, to convert that to polar, you're going to turn this into an r distance, which tells you how far from the origin it is, and a theta distance, which tells you what is the angle from the x-axis to take. And I want to draw a little axes over here. So just to double check, in the xy plane, if I have that green dot, here's my r, and here's my theta. And now I've just spun this around and put it on the xy plane in this other picture. So that's all that's happening. So once you have r and theta, then this new point is determined by theta, r, and z. So this xy, z coordinate becomes the corresponding r, theta, z coordinate. I will say it's kind of common to either put the z first or the z last, and yeah, you should just be clear about which one's r, which one's theta, and which one's z when you're writing them down. So now how do we actually use this for anything? So let's look at kind of some basic graphs that might come up in this setting. So here's 5 graphs. The first 3 are going to be kind of easier, and the last 2 are a bit harder. So this would be a good time to pause the lecture video and try drawing what you think these graphs would be in cylindrical coordinates. So if I give you an equation r equals 2, what is that in cylindrical coordinates versus what is it in polar coordinates? If theta equals pi over 3, what is that in polar coordinates versus cylindrical, etc. So this is a good time to pause. I'm just going to take a quick sip of my tea. Staying hydrated, very important. Life lessons. So now I assume you've kind of all thought through these, so I'm going to work through them quickly. What we have, let me get myself a color. I think I'm going to graph maybe in blue. So r equals 2. In the xy plane, that would correspond to a little circle. I'm going to have problems drawing this. Of radius 2 in the xy plane. But then the z-coordinate is not being specified. So what's happening here is that circle has all of the points in the xy plane that are radius 2 from the origin at every angle theta. Now we also want to add every height z. And so what that will do is give us a cylinder. This is pretty bad drawing. I apologize. And it's a cylinder that's infinite. It just keeps going up and down forever. So it's an infinite vertical cylinder with radius 2. So theta equals pi over 3. In polar coordinates, that's like this 60-degree angle. So it's this angle here. And now r can be negative, so it's also going to go back. And now when we add z-coordinates, we just can shift this line vertically. So what we're going to get is a plane. And it's the plane that's, going straight up and down in some sense. The normal vector has no z component. And it is lined up with the angle pi over 3 in the xy plane. And that's how you could define it. Z equals 2, this is just a plane in like our ordinary way. So if I go 1 and 2 up here in the z-axis, there's another plane. And so some way, the things that are easy to draw in cylindrical coordinates are cylinders, no big surprise there, planes that go through the origin and contain the z-axis. So maybe I should say this, containing the z-axis at a certain angle in the xy plane. And then also just ordinary planes parallel to the xy plane, but at some height z. So this one up here is at z equals 2, where it intersects. Okay, these lower ones are a little bit more complicated, but we can use some of our polar coordinate understanding to figure out what's going on. So I'm going to scroll up a little, give myself a little bit more room. So for the first one, what you should do is focus in on r, and remember that r squared equals x squared plus y squared in polar coordinates. And so if I rewrite this, this is basically the equation in Cartesian coordinates, x squared plus y squared plus z squared equals 10 squared. And that's a sphere of radius 10. Another way to think about this is that at any angle theta, you could imagine graphing your height of the function versus the radius that you are out from the origin at that angle theta. Since this equation doesn't involve theta, at every theta, it's going to have the same picture. So what that means is it's going to be rotationally symmetric around the z-axis, like a sphere. So another way to think about this is r squared plus z squared equals, equals 100. That is a circle. In the RZ plane with radius equal to 10. I'm not saying r equal to 10 because r is one of the variables in this plane. But then take that green circle and spin it around the z-axis, and you'll get a sphere. Now, I've sort of run out of space, and I'm still getting used to using this software, so I don't know how to move z equals r. But this guy over here, if we graph this in the zr plane, this is very easy to understand. So don't even go to x, y's, and z's. This is clearly a line. It's the line with slope 1. So now, since this equation has no thetas, if you spin to get all the different, intersections of this curve as theta varies between 0 and 2 pi, you're going to get a picture of what this shape looks like. And it looks like, well, it's got this line. And then if you spin it 180 degrees over here, it becomes this other line. And as you spin it, it makes a little cone. This is often called a double cone because the cone has, and they extend infinitely up and down. The cone has both the top cone and the bottom cone. So kind of like this upside down cone above a certain height and this like right side up, point up versus point down cones. And you can see that by varying the slope of this line, you could be varying kind of like the angle to which this cone, how pointy it is, right? Okay. So I hope this gives kind of a quick understanding for how graphically we can interpret different equations in cylindrical coordinates. Moving forward, I'm hoping to give you an intuition for when to use cylindrical coordinates versus Cartesian and spherical, which we'll talk about in the next lecture. But for now, let's just kind of conclude with a little general bit for this video, which is, okay, what does this have to do with integrals, which is where we're starting? So if we have an integral, triple integral of e of some function of x, y, and z dv, how do we write that in cylindrical coordinates? Okay, well, provided E is a region that you can make sense of in cylindrical coordinates, you're going to get some sort of bounds over here like this. And the bounds going from the inside out, so the inside ones are the z bounds, and they can involve both r and theta. And then the next bounds are the r bounds, so they can involve theta, and the theta bounds on the outside, which tends to be true with most of these problems, are just between two constant angles. And so an example for how you might draw this region, draw a little bit there. So if in the xy plane you've got kind of like, so let's give myself a couple axes. So here's my z-axis, here's my y-axis, and here's my x-axis. So let's imagine in the xy plane you've got some angle theta, or some angle alpha, and then some other angle beta that your region's between. And now in that region, it's in between two different curves. And so maybe this inner one is h1, and the outer picture of this region is this h2. And I'm trying to draw them slightly wiggly because they can be functions of r. And we'll see some examples later in the lecture. And so in the xy plane, you've got this kind of polar region. And it's often really useful to break these down kind of in each of the coordinates on their own. So in the polar picture for this, just in this plane, what I've drawn is I've got this angle alpha, this angle beta, and then I've got, I think it kind of looks something like this. This one looks almost like a semicircle, or a little bit of a circle, so some constant, r equals 2 function or something like that. And then h2 is doing something a little bit more wiggly, so it's kind of doing something like this. So I've got this region. But in 3 dimensions, that's like the base of the region, and then you've got a lower and upper z height. And so the lower one is u1 and the upper one is u2. So it might be that your actual region is maybe u1 is, to make this easier to draw, is 0. It's just z equals 0, so that would be this lower region. And then above it, it might have some, some other distorted image of what this region kind of makes sense to be. Okay. So you might have something like this. So this top function here would be z equals u2. And you could think of u2 as being a function of x and y, which I've written above this x and this y as r cosine theta, r sine theta. And the same down here for this u1. And you could imagine that if you picked some different values for u1 and u2, some different functions, you're going to get different answers. We will see some examples in the next video.